All right, so let's start from where we left in our last class. In our last class, we actually proved the validity of this iterative algorithm that finds, lets us find the convergence. Now, we ended our last class here with the proof. Now, immediately next comes a theorem 71, which says that let X be a quadratic irrational and X bar be its conjugate, and we know what a conjugate is. Just replace root d by minus root d to get the conjugate of a given real number. The continued fraction of X is purely periodic. If and only if this condition is true, X has to be greater than 1, but its conjugate has to be less than -1, but negative. Well, since X is a quadratic irrational, it is a given that its continued fraction is going to be periodic. That's for sure. The added word, extra word here is purely. It means the cycle will start from the first guy in the, continued fraction expansion, right? So let's try to prove, and of course, this is a two-way argument, if and only if is here. So first, let's suppose that this criteria is true. So we need to show that the continued fraction is purely periodic. Now, how can we prove that? First of all, we are dealing with a real number which is a quadratic root, which is a quadratic irrational number, right? So as I said, it will be periodic for sure. So we are assuming that the periodicity, the cycle starts from this guy AM. Now, all we have to do is show that we can start the cycle from m equals to 0. We can start from here, right? So anyway, how are we going to prove that? Basically here, the cycle length is n, right? AM is equals to AM plus n minus 1. Not equals to this guy, but the guy after that. AM is equal to the guy here. If we can prove that under this circumstance, AM minus 1 is equal to this guy as well. It means that what they're actually, they're giving the terminology downward induction. So using downward induction, we can prove that step by step, we can inductively move down up to as low as A0, right? So what we are going to do is assume that the cycle if the cycle starts from M, we are going to prove that AM minus 1 is equals to AM plus n minus 1. Okay, let's see how we are going to do that. First of all, these guys are all integers, so they are greater or equal to 1 for every I. And of course, we deduce that this is a relation between xi and xi minus 1, which can be rewritten like this. They just took the reciprocal. Now they took the conjugate on both sides to reach to this equation. And there is no conjugate sign above AI because AI is a pure integer. There is no irrational part in AI. Now we are going to use induction to prove that initially you can see that in the given assumption, we claim that the hypothesis is X is greater than 1 and its conjugate is in between -1 and 0. But this is true for X. And what is X actually? If you can remember, X is the overall number whose continued fraction representation was A0, A1 up to, I mean, probably n minus 1. And after that, we are just writing xn. So the thing is, xn is basically someone that starts the part of the continued fraction, the later part of the continued fraction that starts from an. And since we are dealing with irrational numbers, it will keep going on. So this is a sequence of infinite terms. So basically, if we choose n equals to 0, that is the entire sequence, which is x0, which is the same guy as x, then this relation is already true as given in the hypothesis. I mean, this relation. Now, the thing is this true for every I? We don't know that. We are going to prove that using induction. Now, as I already said, I equals to 0 is the base case, and this is exactly the criteria given in hypothesis. So base case is already satisfied. Now, let's assume it's true for I. We are going to prove for I plus 1. Okay. Now, since basically the conjugate is less than 0, but AI is greater than 1. So definitely, if you multiply this inequality by minus 1, you get minus AI is less than minus 1. And we already have xi bar is less than 0. So just add these two, you will get this inequality. And we already know that this guy is just reciprocal of xi plus 1 bar. So finally, this would lead to this inequality. Now, you can understand that basically one x, I mean, if you take the reciprocal on both sides, then we would get, we would get to this point, the left half of the inequality. And already the xi bars are all negative. So that's why this is already true, which means we got to this point starting from here. So inductively, let me clear everything. Inductively, assuming true for I, we prove that it's true for I plus 1. So inductively, we claim that every xi bar satisfies this condition. That is, every xi bar is in between the interval minus 1, 0. All right, so what about minus xi bar then? Xi bar is in between minus 1 and 0. So this guy must be in between 0 and 1, right? Which is given here. Now, we using this equation, if you make xi, using this equation, if you make minus xi bar the subject, you will get that minus xi bar is exactly equal to this guy. Now, here is something interesting. This guy, AI minus AI minus 1 over xi plus 1 bar, this is between 0 and 1. If you add AI on each side, I mean, there are 3 parts of the inequality. On each part, if you add AI and multiply by, take the reciprocal, you would see that ultimately we would get minus 1 over xi plus 1 bar is in this interval, which would actually mean the AI is an integer, AI plus 1 is the immediate next integer, and our guy is someone that lies in the intermediate interval. So our guy must have the floor value AI, right? So why is this helpful? Let's see why this is helpful. We already know that AM plus K is equals to AM plus K plus N, because we saw that starting from this point, the sequence is periodic of period N. So AM plus K is AM plus K plus 1 for sure. And this is true for not just any K, for every positive non-negative integer K. Now, what can we say about XM then? XM we already know starts from N up to infinity. And each of these guy, we can just add an N in the index to find a newer sequence, which is nothing but xm plus n, because it's starting from m plus n, and after that, every next member is here. So we just proved that xm is equals to xm plus n. Now, so far, these are just some claims that we followed, and we have seen that these are true, but why are these calculations helpful? Here it is finally, because as we are trying to prove, this is what we were trying to prove, right? M minus 1 is M minus 1 plus n. Let's see why. M minus 1, according to this statement, if you replace I by M minus 1, you would get M minus 1 is this guy. And since xm bar is xm plus n bar, I am just substituting xm by xm plus n here. And this is nothing but, again using this equation, this is nothing but am plus n minus 1, which proves finally, as we were trying to prove, which proves that if the sequence starts from here, if the cycle starts from here, we can just take one step back to claim that am minus 1 is also equal to this guy, and we can keep repeating this until we reach to a naught, and finally we can claim that a naught is actually equal to a 0 plus n, which is an. So downward inductively we proved that the sequence in the continued fraction expansion is purely periodic. Now we have to prove the other way as well. Now we are going to hypothetically claim that our x is purely periodic, so it has this representation. But we need to show that x is greater than 1, and I mean the criteria given in the other part of the claim. Now the thing is, basically a naught is an integer, so it is at least 1. Then x is a naught plus 1 by a1 plus etc etc. So this is already someone who is at least 1. We are adding something positive here, so definitely x is greater than 1. That's for sure. Definitely x is greater than 1. So x is greater than 1 because x is at least 1 plus some positive numbers. So x is greater than 1 for sure. So this part, let me use another color. This part is easy. It is already proved. What about this one? Okay, to prove this part, they used an interesting technique. We already know x is this guy. And after an minus 1, we are going to repeat the same sequence again and again. So we can just replace the entire rest of the sequence by just x because it's repeating itself. And according to the definition of original definition of pk and qk, it is easy to see that this is just consider this guy as an. Then this is an. This is an and this is an. So this is the exact formula for Pn and Qn, the repeating formula, iterative formula. So we have an equation where the left hand side is x and the right hand side is a rational function, is basically a rational function which has a linear expression of x on the denominator and on the numerator as well. So if you just simplify, multiply this guy on the left and so on, etc. Finally, if you simplify, you will see a quadratic equation like this. Now, assume the entire thing to be a function f of x. Now, f of x is a quadratic here. It has two roots. One of the roots is already x, which is greater than 1. And since all the coefficients are integers, but the root x is irrational number. So we know that if the coefficients are rational, but the root is irrational, then the two roots must be conjugate to each other, right? So if x is a root, x bar must be the other root, right? So, and not only that, if this is true, then that other root is a number between -1 and 0. So just using the bisection method we studied in numerical method, you can understand that if somehow we can prove that f of 0 and f of -1 has opposite signs, that means if you can prove that at 0 and -1, the function has opposite values in terms of sign, that is one is positive and other is negative, it would mean that somewhere in between -1 and 0, there must be the root of the function. So that is why all we have to do is prove that f of 0 and f of -1 are opposite in terms of sign. So what is f of 0? Put 0 everywhere in the equation. You will end up getting minus Pn minus 1, and all the Pi's are positive, right? So this guy is definitely negative. We just now need to prove that f of minus 1 is positive. Put minus 1 here. This is straightforward so far. They skipped one or two lines here. Let me write the lines in between. What is Qn minus 1? The iterative formula says that Qn minus 1 is n minus 1, Qn minus 2 plus Qn minus 3. This is the expression for Qn minus 1. They kept Qn minus 2 intact. So I'm doing that as well, Qn minus 2. Again, they expressed Pn minus 1 in terms of Pn minus 2. So the next term would be, okay, here is a minus 1, minus sign, right? So this should be minus, not plus. This should be minus. Anyway, now Pn minus 1 is again according to the formula An minus 2. Pn minus n minus 1, Pn minus 2 plus Pn minus 3. And there is the last guy, minus Pn minus 2. Now, if you can see, if you take the Qn minus 2 here and here as common from these two terms only, you will get Qn minus 2 as common. The remaining coefficients would be An minus 1, negative 1. So here is An minus 1, here is negative 1. Same treatment with the next pair of terms. They are taking common Pn minus 2. So Pn minus 2 is here, and An minus 1 and negative 1 are the coefficients. The other two terms remain unchanged. Now, why is this positive? All the coefficients are positive. There are just two places where you are dealing with negativity. And that is also not an issue because all the AIs are at least 1 or above because they are positive integers. So there is no way this expression is going to be negative, even though there are a couple of negative signs. So this proves our claim that x bar is in between minus 1 and 0. Okay. Right now, that was the end of that proof. In the next lecture, they recapped the equations we used in an algorithm in our last class and mentioned what we just proved. So that basically what we are doing is actually we are trying to converge to the proof of Brahmagupta-Pell equation. Brahmagupta-Pell equation. Even though they wrote Brahmagupta-Pell equation here, but in the later parts of the lectures they use the shortcut PB equation. So I'm assuming that this is the place where this swap the order, and this is the original order. It's known as, that is Pell-Brahmagupta equation. So I'm considering Pell-Brahmagupta equation as the name. So what we are doing now is actually trying to establish the background to prove Pell-Brahmagupta equation. And from what basically Pell-Brahmagupta equation is something that looks like this: x square minus x square minus dy square is equal to 1. This is the most common case of Pell-Brahmagupta equation. This equation may or may not have solutions, right? Consider it as a Diophantine equation. The solutions should be integers. Here is a condition that d is not a square, and in the lecture notes they are writing this in a very shortcut and interesting way. They are writing that d is not a square. Okay, so d is an integer, but it's not a square of any integer. And what they are trying to prove is that if there is any integer solution for this equation, or if exists, then are there finitely many or infinitely many, or what are the conditions under which the equation has solutions, etc. And there is a more general form of the equation where they use some integer n on the right hand side instead of 1. But the most common case is considering 1 or -1 on the right hand side. So let's see how things that we are studying currently converges to the proof of those claims, or how these are related to that equation. A direct corollary to the theorem we just proved is they're claiming let d be a positive integer, not a perfect square. Then the continued fraction of this interesting number is purely periodic. Okay, this is a very interesting number, right? So you're taking the square root. So this is a very, very rational number. And they're taking the floor of that number and adding it to the original irrational number to make a nice looking irrational real number. And they're claiming that the continued fraction of this guy is purely periodic. So the cycle starts from a0. Let's see why this is true. The proof is pretty simple. First of all, even if d is the least positive number that is not a perfect square, that is, I'm claiming even if d is the smallest value it can be under the conditions, that is 2, then √2 plus floor of √2, which is approximately 2.414, etc., which is greater than 1. So x is greater. You should be able to see what we are doing. We are using the last theorem we proved. And that theorem claims that the right to left direction, it uses the right to left direction of the theorem. That is, if you can see that our x is greater than 1, and its conjugate is someone lying in the interval -1 to 0, then the continued fraction x should be purely periodic. So we are trying to prove that our guy, this interesting guy, follows the criteria. Okay, so definitely this is greater than 1. Its conjugate, I think there is a mistake in writing the conjugate. It should have plus here and minus here. So this is the conjugate of the given number x. Why does it satisfy this? You can see that the floor of √d has to be less than √d, of course. And if you add 1 with the floor, it will be the ceiling of √d, of course. So √d is in between these two guys, which would just mean if you subtract floor of √d from each part of the inequality, you will see that our x bar is someone in between -1 and 0. So since our guy x fulfills the condition in our last theorem, then it must be purely periodic. Now, here is another claim. What they're saying is this was our guy in the last corollary. Technically, it contains a 1 as the denominator, right? Then compare it with the structure of the algorithm, B0 plus √d by C0. You can see that B0 is, another mistake, I think. B0 has to be floor of √d. So B0 is floor of √d, and C0 is just 1 here, and √d is just √d. Then we want there, it is purely periodic, we just proved. So its representation should look like this, considering that the period of the cycle is r. Then say, for example, definitely if something looks like this, if a continued fraction looks like this, you can claim that this is this is the part that's repeating. You can also claim that this is the part that's repeating, but there has to be someone who is the smallest cycle possible. They are considering that this is the smallest case. Then their claim is each of these numbers x0 up to xr -1 are distinct. This is pretty straightforward actually, because if they were not distinct, then x0 has to be equal to some xi where I is someone less than r -1. There has to be some repetition somewhere, right? If they are not all distinct. Then we would have the period I, which is smaller than r, which contradicts the minimality of r. So this was pretty straightforward. Now, we are going to take another step forward towards Pell-Brahmagupta equation, and we are going to prove that, say for example, these x naughts are xi's are all the xi's in that, I mean, bi plus root d by, say, all those guys in the in the algorithm we learned in our last class. Okay, so they are claiming that xn equals to x naught if and only if n is a multiple of r, which should be true because, I mean, we are dealing with repeating case. The smallest period is r. So as I wrote an example here, 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. So either you start from here up to last point, or you start from here up to last point, or you start from here up to last point to get the same value. But you cannot just start from here and claim that this should be true, exactly equal to what we get if we start from here. So we have to start from an end point of a particular cycle, which means that n should be a multiple of r, right? Okay, now they are claiming that Cn is equals to 1. This is the most important proof probably while we are trying to establish the background of Pell-Brahmagupta equation. Cn is equals to 1 if and only if n is a multiple of r. This is first part of the claim. And second part of the claim is Cn can never be minus 1. So let's move on to the proof. First, we prove this part, and you can understand that this is a two-way argument. So first, assume that n is a multiple of r. So n is kr. We are going to prove that Cn equals to 1. Let's see how they're doing it. So basically, n is already kr, right? So I replaced n by kr here. I mean, they replaced, not I did not do that. They replaced n by kr, which is the expression for xkr, right? And since n is a multiple of r in this case, so n has to be equal to x naught. And what is x naught? Our first guy, the number of which we are trying to find the continued fraction. So this is our guy. So the thing is, this left-hand side is equals to this right-hand side. So they are just cross multiplying and rearranging to get this expression. And in this expression, if you basically, when do you, what is the, can you see that the left-hand side is purely integer? BKR and CKR are by definition integers, and since you took floor here, this is also integer. But the right-hand side is not integer because of this root d. And we are never going to produce a root d in this expression because CKR is integer. So the only way this is going to be true is if CKR is equals to 1. So this is the only way it's going to be true. So this proves that Cn equals to 1. Now let's prove the other way. Consider the Cn is now 1. We have to prove that Xn is this guy. Okay. We are going to, basically now we are considering that Cn is equals to 1, and we are going to prove that n is a multiple of r. Let's see how we are going to prove that. Cn equals to 1 and Xn is purely periodic, because not Xn, because the cycle starts from n, right? If you start the cycle from n, we are going to basically the entire continued fraction is purely periodic, because we just proved as a corollary that this produces a purely periodic continued fraction. So yes, we know for sure that this Xn is purely periodic. Now Xn is greater than 1 and minus 1, this was already proved, right? So these are given in a way. So what is Xn bar? We have X, since Cn equals to 1, there is no denominator. Xn is just Bn plus root d. Then what should be its conjugate Xn bar? Just put a minus sign here as they did, right? Now this guy is greater than minus 1, less than 0. what we are doing is actually adding b. Just subtract bn from everywhere, and then multiply by minus to get this inequality. So bn and bn plus 1 are two consecutive integers, and root d lies in between. It proves that floor of root d is bn and ceiling of root d is bn plus 1. We don't need the ceiling, we need the floor. So bn is just floor of root d, which means replace bn by floor of root d here to get xn is this guy. And if xn is this guy, which is exactly equal to x naught, this just means that it's repeating after n places. So n must be a multiple of the original period r. This proves our claim, only first part of the claim. The second part or last part was that Cn cannot be minus 1. We have to prove that as well. Let's see. Suppose, consider that Cn equals to minus 1. We are going to produce a contradiction and claim that Cn cannot be minus 1. So xn is bn plus root d. So basically Cn is minus 1. So xn is bn plus root d divided by minus 1. That is why we have minus here and minus here. Now, this is purely periodic, and so this these two inequalities are true from the corollary, from the theorem we proved at the beginning of our class. Now, xn is greater than 1 implies, just substitute xn, substitute this guy in place of xn to get this inequality. And here is another inequality, just substitute xn bar by bn. This is, xn, if you want to find xn bar, just replace the minus by plus here to get this guy. So we have two inequalities, one is here, one is here. Can you see this just means, from here, bn is greater than 1 plus root d, which is greater than just root d. So bn is definitely greater than root d. Again, from the second inequality, you can see that bn, using similar calculations, you can see that bn is less than minus root d minus 1. So basically, bn is, at the same time, it's greater than root d, but it's also less than minus root d minus 1, which is absurd, because that would mean this inequality has to be true, which is absurd. So we produce the contradiction, so Cn cannot be negative. Negative 1 particularly. Cn, maybe it can take other negative values, but never minus 1. Now, here is something that looks like pretty useless here, but this is going to be useful within a couple of minutes actually. We have been dealing with this interesting number. Now, what is the floor of this number? In the algorithm, we have seen that AI is actually floor of xi, right? So a naught is floor of x, but what is the floor of this number? You can see that this part is integer, so it actually does not affect, the outer floor function does not affect this guy. It only affects the guy here. So when distributed, writing double floor here would not mean anything. So that is why they did not write that. So we have one floor of root d here, another floor of root d here. Adding, we get twice of floor of root d. So what should the continued fraction of this interesting guy look like? It starts from, we have seen the starting value a naught is just this guy, right? And then a1, we did not find what a1 and other guys are because we are not interested in them. We are just interested in the starting value. So it has a period of r. So it starts from a naught and ends at ar minus 1. Everything is fine so far. So all we did just actually found the first value in the sequence. Now this can be written like this. Just start from this guy and start the cycle from a1 so that you are repeating this guy again here. So we just shifted the cycle by 1 unit, and this is fair, right? We are repeating this guy again after this a1 comes, so it's all right. We can do that. But what about the continued fraction of just square root of d, not this guy, but only square root of d. You can see that basically square root of d and square root of any number x and x plus, for example, 5, what is the difference between their continued fractions? The only difference is going to be these two guys have no difference in their fractional parts. Only difference is in the integer part. And in continued fraction, all we do is take the integer part, separate it from the fractional part, right? So the difference will only be in the first value. If this guy has the first value a naught, and second value a1, that means it would go like this, etc. This guy would have the representation, its integer part is going to be just add 5 to the original value. Then the fractional part is the same for these two guys. So the second guy will be exactly a1, just like here, and so on. So the only difference will be in the first guy in the sequence. So this integer is being removed when we are considering root d only. So the difference will be the first guy will be reduced by this much value. So 2 times floor of square root d minus a single floor of square root d gives us this guy. Let me know if this part was clear to you. Okay, if this was clear to everyone, let me move on. So basically, the remaining part will be same, and the period should be then of exact length r. So this is that period of length r. So this is definitely not a purely periodic expansion, right? Because this guy is never repeating. It starts its cycle from here. So you can see that even though the period of the two guys are same, it's exactly r, but the cycles start 1 unit later in case of root d. And this is going to be important in our next proof. Our next proof actually says that next theorem claims that if d is an integer, positive integer which is not a square, and if these are the convergence to root d, and Cn is the sequence of integers we define for x. Basically, Cn is what you already know, right? We are starting with x naught. Since the number is exactly root d, our x is exactly root d. So x naught is just 0 plus root d by 1. So b naught is 0, c naught is 1. And starting from here, if we use the algorithm, then they are claiming that this needs to be true. Pn square minus dqn square is minus 1 to the power n plus 1 cn plus. This is not choose, right? This is not permutation combination. This is just times c index n plus 1. You can understand that actually. Okay, how can we prove this? And if this is true, can you realize we are very close to Pell-Brahmagupta equation? If this is true, then we can almost, it almost looks like if, for example, n is odd, then n plus 1 is even. If n plus 1 is even, then we have a 1 here. And also, if n is a multiple of r, then we can claim that this guy is 1. Can you remember why? Because of this, we already proved Cn is not minus 1 and Cn is 1 if and only if n equals to k. So if n is a multiple of the original periodicity r, then this guy will be 1 as well. So the entire right hand side will be 1. It would mean that Pn comma Qn is a solution of the Pell-Brahmagupta equation. And what is Pn comma? Okay, this was the same old 40 minutes issue with Zoom. So let me continue from where I left, where the Zoom left us actually. What I was saying that since under some conditions the right hand side can be 1, it would mean that in those situations, under those criteria, Pn comma Qn is a solution to the Pell-Brahmagupta equation. And who are Pn and Qn? The answer is Pn by Qn is the convergent to the continued fraction of root d, convergence to root d. So all we have to do is find the continued fraction of root d up to some in iterations, and at each iteration find the convergence, that is pi by qi, and for the index, for those particular index I, the right hand side is 1, will give us the solution of Pell-Brahmagupta equation. This is pretty interesting actually. So let's see how the proof is. The proof is pretty simple, to be honest. First of all, we can see that root d is x, which is the first value x naught, right? Now, why are they using n plus 1 here? They are using n plus 1. That means they are claiming that x is a naught, a1 up to an, and here they are replacing an plus 1 by xn plus 1. The periodicity is n, right? The cycle length is n, so the replacement should have done here, but they are doing it on the next guy, just because, as you can remember, the first guy is not a part of the cycle for root d. The cycle started from a naught for root d plus floor root d, but in case of root d, we have seen that the cycle starts from 1. So that is why to get n terms, I have to go as far as an plus 1, or I mean xn plus 1, since we have replaced the entire remaining sequence by a single term. Okay, so then from the formula of Pn and Qn, you can see that this is just this guy. And after that, the calculations are pretty easy. Basically, what they're doing is, from the algorithm, they are replacing xn by this guy and this guy. And then they're simplifying by multiplying Cn plus 1 both on numerator and denominator to get rid of fraction within fraction. And then they are just actually separating the rational and irrational parts both on numerator and denominator. After that, they're multiplying this guy on the left. So root d times root d becomes d, and so on. This is that d, etc. So after multiplication, what we can do is compare coefficient. Coefficient of what, by the way? Coefficient of the rational and irrational part, actually. So on both sides, the rational part on the left side is this guy, and rational part on the right hand side is this guy, which gives us this equation. But where does the square come from? Simply, okay, basically from the rational part, they are writing the second equation. But why is there a qn square instead of qn? What they did is multiplied qn on both sides as well. And of course, the irrational part, I mean the coefficient of root d is on left this one, and on right this one, and equate them, and finally multiply by Pn to get this equation. So we have these two equations, and you can understand that we are interested in the expression here on the left hand side, Pn square minus dqn square, so that we can prove that this guy equal to actually this guy. So that is why they are subtracting these two equations. And after subtraction, on the right hand side is what we seek for. And the left hand side, you can see that these two guys gets cancelled. Do they? Pn plus 1 times Qn minus Pn. Why is it no longer there? Why is it 0? Oh, not really. There is another Pn here. After multiplication, the two guys become same. So they do get cancelled. So yes, these two gets cancelled. And from these two, take Cn plus 1. Here we should have plus 1. Cn plus 1 is common. This remaining part is, in our last class, we proved that this is actually minus 1 to the power n minus. Basically, n minus 1 and n plus 1 on power of minus 1 works same. So this can be written as plus 1 as well. So from there, we already got what we wanted. The proof is completed here. Now, as we have anticipated, the argument will come where n is a multiple of r and n plus 1 is even, etc. So the corollary is here. If r is the period of continued fraction expansion of root d, then from this, the direct result byproduct is this guy. There is a lot of type actually. This r should be beside k, not here. Minus 1 whole to the power kr. The r should not be a product of minus 1 to the power k, but only k. Okay, basically, you can understand why this is true. We have already mentioned. That is, if you consider n to be kr, consider n to be a multiple of r. If you consider n equals to kr, then this guy becomes 1. And basically, we are not considering n to be kr, but 1 plus n to be kr, because remember that we skipped the first guy. So 1 plus, if 1 plus n is kr, then what is n? Kr minus 1. So replace n by kr minus 1 to get the left hand side, these two. And on the right hand side, since n plus 1 is a multiple of kr, this is 1, so no point in writing it. The remaining part is minus 1 to the power kr, which is what written here. Now there is a remark now, of course, at some point we were to go there anyway. If kr is even, then the right hand side is exactly 1. So which means that these particular values where whenever n plus 1 is a multiple of r, we get a solution pkr minus 1 qk minus r minus 1 of the Pell-Brahmagupta equation. And there are infinitely many, because for each multiple k, I mean for any integer value of k, you are going to get a solution, because the only condition is n plus 1 is a multiple of r, any integer multiple of r. So any integer multiple of r will do. So just put k equals to 1, 2, 3, and so on to get infinite number of solutions. Okay. Now the next step is the Pell-Brahmagupta equation actually. So let's directly step onto that. First of all, observe that if our equation is like this, and somehow if d is an integer which is not a square, if d is negative, we are given an equation like this. D is an integer, x, y's are also integer, each of them can be positive or negative. But if d is negative, then d can be replaced by minus modulus d. That's high school idea, right? And now all of the terms are positive here, and adding them, you are going to get 1. And this is not a modular system, right? So there are only finitely many possible solutions for this equation, if there is any. It's possible that there are no solutions. If d is 100, then there is no way you have. Yes, there is a way you have a solution. If d is 100, just put y equals to 0 and x equals to 1. So you will get the trivial solutions in those cases. Okay. Now, so d less than or equal to 0 is not really a big deal or any big issue for us. If d is positive, then this equation may produce infinitely many solutions. So in that case, we are concerned, and that is why. Anyway, our main concern is positive values of d. This is what I'm trying to establish. Anyway, now step on to a bit more general case where we have already mentioned, instead of 1, put n on the right hand side. So in this case, as you can see, if any xy is a solution, then all these 4 guys will be solution, right? X comma minus y, x minus x comma minus y, all of them are going to be solutions. So if you just produce the positive solutions, you will get 3 more for each solution. So this actually motivates us to consider only positive solutions, first of all. I mean non-negative solutions. Also, putting, just like in this case what we did here, put x equals to 0 to get some, if positive integer values of y possibly, if there is any, and put y equals to 0. These cases will produce trivial solutions, right? So we are not interested in 0 cases as well. So we are mainly interested in strictly positive values of x and y. Those are of our main interest. Now, We can also safely assume X and Y are co-prime, because if they are not, and if their GCD is G, we can easily divide both sides of the equation by G square, because if X and Y have GCD G, then X square and Y square will have GCD G square. And that G square has to divide N, otherwise there will be no solution. Just like congruence equation we studied in our early classes of this semester. So G square has to divide N, and if that divides N, then divide both sides of the equation by G square to get to a situation where indeed GCD of X, Y are 1. So even if the GCD of X, Y is not 1, we can produce a situation where their GCD is 1 just by dividing by their GCD square. So this, and the solutions where co-prime solutions has a nice name, they are called primitive solutions, right? So the final conclusion is we are interested in only positive solutions and primitive solutions. So positive primitive solutions of this equation is what we are looking for. And a theorem lets us do that. Consider positive integer value of d, which is not a perfect square, and consider an integer n less than z where its absolute value is less than square root d. Then any positive primitive solution xy of this equation has the property that x by y is a convergent to root d, which we actually kind of claimed here. The only difference is here, in this case, the right-hand side was 1, not n. So we have some proof to do here. Suppose they are claiming rho is a positive real number such that root rho is irrational, and sigma is any real number, and st any two positive integers such that this equation is true. You can see the resemblance with this equation, right? They are somehow comparing x, y with st. They are comparing d with rho, and they are comparing n with sigma. So what they're doing, since absolute value of n is less than root d, and here they considered sigma to be positive. So taking absolute value is not a requirement here. So they are just taking sigma to be less than root rho. Their claim is this difference is less than 2t squared. Now, why this claim will be useful? Because let me go back many steps. Give me a moment, please. Because of this theorem, of one of every two consecutive convergence satisfies this equation. If Pn by Qn is a convergent, then their difference has to be less than 1 over 2 Qn square. Qn is the denominator here. Compare this inequality with what we had there. This is the denominator t. We have 2t square here. So if this is true, then we are very close to the proof that S by t is indeed a convergent to our guy root t or root rho in this case. What they're using is, start with this guy, take the LCM and multiply by the conjugate of the numerator on both numerator and denominator to get a square root free expression in the numerator. But there will be a square root expression here anyway. And what is s square minus t square rho? It is just sigma from the original equation. So this is just sigma. So what they're doing is, since sigma is positive, so this entire guy is positive, this entire thing is positive, and these are just positive numbers. So this entire thing is positive. So taking the modulus is does not matter actually. So this entire thing is positive, which means this guy has to be positive. So S has to be greater than t root rho, first of all. Now add t root rho on both sides to get S plus T root rho is greater than twice of T root rho. I'm just adding T root rho on both sides of this inequality. So that this guy, as we have seen, is already positive. This, there is another typo, this should be product. So they are directly using this guy instead of this guy. This can be replaced by this guy, and this guy here, the S plus T root rho is, as we have just, the denominator is actually greater than T times 2T root rho. So the only the denominator is greater than this guy. So if you take the reciprocal, the direction changes. So less than sigma by T into T 2T root rho, which is 2T square root rho. And sigma is also less than rho. So see, if you replace sigma by rho, then the inequality still holds its direction. So root rho gets cancelled and we have 2t square here, which proves our claim. Now this actually does not actually explicitly prove that this S by t is a convergent to root rho. But for example, this actually does not prove that Pn by Qn minus root d. If x by y is indeed a convergent, it would mean that x by y can be replaced by Pn by Qn. T or rho, whatever, less than 1 over. So it would, we need this guy actually to prove that x by y is a convergent or exactly equal to Pn by Qn for some n. We did not prove that, but this can be done easily if you, I mean, if T is not any Qn, then you can consider that there exists at least one value of n for which T lies, oh my God, T, give me a moment, please. If T is not any of the Qn, then we can find at least one value of n so that T lies in between two consecutive Qn's. And considering this will produce a contradiction, and that would lead to us that S by T has to be a convergent, has to be Pn by Qn for some n, which will complete our proof. Now using the claim we just, as they are saying here, using the claim, we can see that S by T is a convergent. As I said, this is, they did not provide a proof, but using that contradiction, we can fill the voids in between these two steps. And after that, it will be proved that S by T is a convergent to the continued fraction of root rho. Now, if n is a positive number, you can just replace I already did the comparison, right? You can just replace sigma by n, rho by d, and this is not GCD, this is ordered pair ST by ordered pair XY to show that X by Y is a convergent. So if n is positive, then we are done. Why is this important? Because as you can see in the original proof, n was not necessarily positive, but in this claim, they considered sigma to be positive. They did not do anything for negative sigma. So that is why they are just claiming that if n is positive, then the above proof is enough. But what about negative n? If n is negative, we can just rewrite this equation, multiply both sides by negative so that the right hand side becomes a positive integer. And then here we have coefficient 1 and we have coefficient d. So here we must have coefficient 1 and here we must have coefficient some number not equals to 1. And that can be done because if you just multiply by minus, you would get dy square minus x square equals to minus 7. So we don't have 1 here, we don't have not 1 here. To get rid of this situation, just divide by d to get this final form. Now the right hand side can be considered as sigma, and in this case the absolute value of n is actually less than root d. This has to be true to apply the proof we just did, and this is indeed true because sigma is less than I mean, for the above proof, sigma has to have an upper bound which is exactly equal to the root of this guy, right? And here this is true as well, because since in the original proof claim of the theorem, absolute value of n is less than root d. So here sigma has to less than minus n by d, which is less than, since n is negative, so minus n is positive, so we can consider this to be just absolute value of n, and it has upper bound root d by d, and this is equals to 1 over root d, exactly square root of this coefficient. So sigma satisfies the condition as well. So we can now just apply the above argument and say that not x by y, but y by x is a convergent to the real number, not root d, but 1 over root d. But we are not interested in 1 over root d actually. We are interested in root d. So what is the relation between the continued fraction of root d and that of 1 by root d? This is pretty simple. If root d has this continued fraction, then what about 1 by root d? It is just 0 plus 1 by root d can be expressed as a0, a1, etc. So this is just, it starts from a0, right? But there is just one extra term at the beginning. So that is why this can be written as 0, a0, a1, etc. So if root d has this expansion, 1 by root d will just have an extra 0 at the beginning, right? You can see why this is true. So in that case, as you can see, this 1 by root d has this is 1 over root d. This has this expansion. The 0 is omitted here because adding 0 does not add any value. And this is exactly the convergent pk by qk. So the convergent for this guy up to k terms is just reciprocal of 1 by pk by qk, which is qk by pk, which actually tells us that if y by x is convergent to 1 by root d, then x by y is convergent to only root d, which was the same result for n positive. So in either case, n positive or negative, we can just find the convergence of root d and seek the solution of Pell-Brahmagupta equation in those convergences. Many of those convergences are going to be solution of the Pell-Brahmagupta equation, and this is here they are mentioning that claim actually. If d is a positive integer, not square, all positive solutions to this equation are of the form this, where Pn by Qn are convergent to root d. And if R is the period of the continued fraction root d, then for even R, this equation does not have any solutions, but the positive one, if the right hand side is +1, then it has infinitely many solutions, which is of the form pkr minus 1, qkr minus 1 for every value of k. And if R is odd, then all the positive solutions of this guy is given by the same expressions, but for values k of equal to 1, 3, 5, the odd values of k only. And if you choose the even values of k, you will get the solution for the case where the right hand side is +1 instead of -1. Basically, whatever written here has already been proved by argument, through argument by us in the earlier part of our class today. We already proved it, right? Using this expression -1 to the power n plus 1, n plus 1. We have done that already. Basically, the -1 +1 are going to be this. If R is even, then we don't need to depend on k. The right hand side is already positive. And since R is even, the right hand side is never going to be negative, which proves the claim here. -1 has no solution, but 1 has solution for every k. But if R is odd, then we are dependent on k. If k is even, then we have solution for +1 case. If k is odd, then we have solution for -1 case. So all of them are done. We are almost at the end, of our class today. The last thing we are going to prove is this theorem. Oh, before that, there is a very small remark. if we have two solutions, x1, y1 and x2, y2 of the equation this, then if x1 is less than x2, y1 has to be less than y2 as well. So we are in a increasing situation. We are never going to get solutions where we are never going to get positive solutions where x1 is greater than x2, but y2 is greater than y1. This is never going to happen. If one increases, the other increases as well. And it's very easy to prove. I mean, if we are consider y1 less than y2, this would mean, what is x1 square from this equation? Just 1 plus dy1 square. And since y1 is less than y2, y1 square is less than y2 square. So 1 plus dy1 square is less than 1 plus dy2 square. And this is the expression for x2. So we have x1 square is less than x2 square, and we are not dealing with negative numbers here. So we can just safely square root on both sides of the inequality to get x1 is less than x2. And the argument for the opposite direction is same. Now the last theorem, as I was saying, this is pretty interesting. Generally, in cases where we have infinitely many solutions, we always look for a situation if there is any situation that from one solution we can generate all the other solutions. And we have solved linear Diophantine equations using similar idea, right? We used Euclidean algorithm to get just one solution. All the other solutions were developed from them using the GCD, right? So here the situation is similar actually. If x1, y1 is a solution, if x1, y1 is a solution, and maybe if it's the least positive solution, and then there is no ambiguity in the term least, one would argue that who is least here, x1 or y1? There is no ambiguity there because we just proved that they are going to behave similarly. So if x1 is least, then y1 is least as well. So if x1, y1 is the least positive solution of the Pell-Brahmagupta equation with right hand side plus 1, then all positive solutions are going to be given by xn comma yn. This is very interesting, where xn plus root dn is just x1 plus root dy1 whole to the power n. Kind of looks like Euler's equation. They gave just one example, but we are not satisfied with the example. Of course, we need the proof, and the proof is given in the next lecture. Why is it stuck there? Oh. Yeah. We are going to the next lecture for this proof. The proof is interesting and simple. We have to prove that all solutions are given by this. So first of all, let's see that this is a solution, and then we shall prove that every solution has to be of this form. First, let's see if this is a solution. We are considering x1, y1 as a solution. That means this equation is true. Factorize the left-hand side using the formula of a square minus b square to get this. So this is an equation we are going to use. Now, the definition of xn and yn is given by this equation. What I'm doing is taking the conjugate on both sides to get this guy. And I'm multiplying these two equations to get this product is equals to this product. But the n can be above the overall product. N can be brought here, right? And these will produce exactly this equation. I mean, basically this guy equal to 1. So we just proved that these two conjugate has product 1. Which means actually, what is this product actually? Xn square minus dyn square. So this is equals to 1 means xn yn is indeed a solution. So this part is done. Now the main part. We have to prove that all the solutions must be of this form for some n. How can we do that? First of all, try to realize that first of all, they claim we are going to produce contradiction. Let's assume ST is a positive solution, but not of this form for any n. Then they're claiming that this guy is positive. Why is this positive? Basically, this is greater than 1. Why? Because S, and we are dealing with positive numbers. So S is already greater or equal to 1, and we are adding something more. So the overall number is greater than 1. Okay, now this sequence is an increasing sequence that can reach up to infinity, right? Because this guy is this guy to the power n, and in here we have something that is less greater than 1. So taking n tends to infinity will produce infinity. Okay, now basically if this is what this means is for increasing value of n, these guys are increasing as well. So definitely if s plus t root d is not any of the guys of this form, then we must have two consecutive n and n plus 1 for which s plus t root d lies in between these two consecutive solutions. Not really solutions so far, I mean two consecutive guys, I mean. So what I'm doing is multiply this entire inequality by this particular real number, which is the conjugate of the left hand side. So after multiplying on the left hand side, we would get xn square minus dyn square, which is exactly 1. We have already seen this is a solution. In the middle, we get s plus t root d times our multiplier, which is this. And the overall product is going to be of the form sum a plus b root d from high school algebra, right? And a, b are integers. And on the right hand side, rightmost side, we have this guy multiplied by this guy. But as you can see, the power n plus 1 can be taken above here. Also here, the power n can be taken above. And of these n plus 1 terms, use n of those to multiply with these to produce 1 using similar logic. Just one odd man remains from this n plus 1 guys. So the overall right-hand side becomes this. Finally, we get to a situation where we have one less equal our a plus b root t, where a and b are integers, less equal this guy. Now we will see that ab, if a we consider, I mean, if ab, we will see that basically we know that a and b are integers, but we are not sure if they are positive integers. That is why we are going to now prove that they are actually indeed positive integers first, and then we will produce a contradiction up to the minimality of x1, y1, so that our proof gets completed. So consider a plus b root d. It is just 1 over a plus b root d because their product is, y. Now, this is a typo here. A minus b root d a minus b root d is greater than 1. A minus b root d is greater than 1. So this guy is a minus b root d is less than 1. So this guy is actually less than 1. Not really. Not really. This is greater than 1. So the reciprocal has to be less than 1. This is a typo. This should be less than 1. So we have an inequality here. And also we have another inequality, which one? Basically a minus b root d is less than 1 here. So this should be less than 1. Where is the confusion? This should be less than 1. Because this guy, a plus b root d is greater than 1, so its reciprocal should be less than 1. So definitely we have a typo here. So a plus b root d is actually less than 1, first of all. And what about a plus b root d? This guy is greater than 1. So, but this guy is greater than 0. So we have a plus b root d greater than 1 from here. And we have since this is less than 1 and this is positive, from here we have a minus b root d greater than 0. Adding these two, These gets cancelled. We get 2a is greater than 1. So a is greater than half. That means since a is integer, a is greater or equal to 1. So a is definitely positive integer for sure. It was guaranteed that a and b are integers, but it was not guaranteed that they're positive integers. We have proved that a is positive integer. Again, what is b, by the way? Take b as a subject in this inequality. So a minus 1 is less than b root d, and root d is a positive number, so we can divide by that safely. So b is greater than a minus 1 by root d. Now a is greater or equal to 1, so this is greater or equal to 0, which proves that b is also never going to be negative. So both a and b are positive integers, and they are solution, but definitely a is less than x1 and b is less than y1, which contradicts the minimality of x1 and y1. So all the solutions has to be of the given form, which completes our proof. We are going to have a class on 15th April, and at the middle of the class we shall take the quiz online. I shall provide the question in the middle of the class at about 9. The class will start at 8:15 in the scheduled time, just not physically but through Zoom. So I shall see you on 15th April, I mean Saturday at 8:15, and we shall continue from here. 2 days, I think I should close the class today for now. If any of you have any confusion anywhere so far? All right. Okay, see you on Saturday then.